Hi, this is a presentation of the distance vector dynamic routing protocols. And when we look at the distance vector routing protocols, they exchange information about how to reach a remote network. And they do that by using a vector, which is a distance, or a direction, and then a distance of how far away is this network. And by exchanging these informations, the routers also shares information with their neighboring routers. And the whole idea here of the distance vector protocols is that you exchange with your neighboring routers. And they use that information to learn about remote networks. And when they detect a topology change, that a network stops working, for instance, well, then this information will also be received by all the network or all the routers that we are connected to. This is the whole idea of having a dynamic routing protocols, because all this information will get get into our networks automatically. So when a router boots up, like we have in this slide here, we will see that by default they know about their own directly connected network. So this is when we boot up and cold start all the three routers that we have here. So router 1 knows that I have a directly connected network called 10.1.0.0 and I have 10.2.0.0 that I'm directly connected to. Same thing, R2 knows that I know of network 10.2.0.0 and 3.0.0, and 3 knows about 10.3.0.0 and 4.0.0. So these are all the ones, and by default, the minute we configure a interface on our router with an IP address, this information will go directly to the routing table. So we will be able to see that we have these directly connected informations. Then, when we have a routing or a distance vector routing protocol here, the routers will then now start to exchange information with their neighbors. So the router sends an update packet with its own routing table to all the interfaces that we have configured to use this dynamic routing protocol. And then it will receive this information and it will update its own routing table. So for instance, router 2 gets an update from router 3 about the network 10.4.0.0, for instance. And in the update, we will see that 10.4.0.0 in router 3 is in 0 hops, which means that it is directly connected. And router 2 knows that router 3 is a neighbor. And then if it says that if my neighbor can reach this network in 0 hops, then I can reach it in 1 hop. And the same thing applies to the remote network on router 1, which is 10.1.0.0. This update will also get into the routing table of router 2 with a hop of 1, because it's something that my neighbor can reach. So this is the first step. The second step is also when you get the information on router 1 about networks on router 3. For instance, the 10.4.0.0. This information will then reach router 1 in the next update that will be sent, because router 2 now knows about 10.4.0.0 and it can reach that in 1 hop. And that means that router 2 exchange this information with router 1, which then updates its own routing table and say that, okay, then I can reach 10.4.0.0 in 2 hops. Of course, we do not want that this information about 10.4.0.0 will go back to the network, so that router 2 or router 1 sends the information back to router 2 and say, okay, I can reach 10.4.0.0 in 2 hops. And then R2 will say, okay, then I can reach it in 3 hops, because there is something implemented which is called split horizon. So split horizon prevents information from being sent out to the same interface on which it was received, so that if R1 receives information about 10400 from R2, it will not be sent back to R2 again. So that is called split horizon, and it's something we use to avoid loops in our network. And at some points, in this case here, we only have 3 routers, so it will take only like 2 updates, and then we are all what we call converged. Converged is when everyone knows about all networks in the entire network. So we can rate them, the routing protocols, on how fast they are at convergence, and distance vector routing protocols are slow to converge, because typically we send out the entire routing table to our neighbors, and we only know about the neighbors. If we look at the distance vector routing protocols, we have RIP, and we have IEGRP, and we have different versions of the IGRP. IGRP is a Cisco proprietary protocol. It's an old one, so we no longer use it, but then we have made the EIGRP, which is, you know, a newer version of the EIGRP. And we have RIP version 1 and version 2. RIP version 2 is the one that we use because it is a classless routing protocol. It will understand when we are using subnetting, for instance, or summarization in our networks. RIP version 2 also uses multicast addresses when it sends updates out, instead of using broadcast. And RIP sends out periodic update, which means every 30 seconds they will send an update about the routing table, whereas EIGRP sends out updates only when needed and not all the time. The distance vector algorithm is quite simple. It will just, it's something called the Bellman-Ford algorithm, but it will just find the best path by using, for instance, how many hops that we will need to get to a remote network. EIGRP uses something called the dual. It's more complex, the way that it will calculate the best path. Yeah, so when we look at RIP, it is very, very simple to set up. It has a maximum hop limit of 15, because the time to live is set to 15 when we look at RIP version 1, and actually also version 2. When we have RIP for IP version 6, we also have the hop limit of 15. So it's for very small networks. We see that RIP version 1 will not support any kind of summarization or subnetting, whereas RIP version 2 will do that. RIP version 2 also send out updates on a multicast address instead of a broadcast. And RIP version 2 also supports authentication. So if I want to authenticate my updates. When I look at the same thing, almost applies when we look at EIGRP and IGRP, which is replaced in 1992. So it's EIGRP is very, very old. And EIGRP also supports subnetting and supernetting and authentication, and it uses also a multicast address. This is faster than RIP because it converges faster, and it uses more resources than RIP because the calculation of the best path is more complex. Yeah. And that was it about the distance vector protocols. Thank you.